So as I said, to understand these identities, we want to not memorize them, but really understand them through practice. And so we're going to take a look at Rosen's Table 6. So if you don't have it pulled up in your textbook right now, I'm going to put it right up here on the screen. And we're going to get some practice with applying a few of these identities. And there are a bunch of different ways that we could apply them. For example, one is in simplifying compound expressions. So we might want to simplify this compound expression right here. So if we want to simplify this compound expression by using these identities, let's go ahead and see if we can do that. Well, when I simplify some compound expression, just like in algebra, there's not just one single way that you can go about simplifying it. There's a bunch of different ways, because you might be able to apply some of these identities in different orders and in different ways. And at the end, you're going to get the same or similar looking logically equivalent expressions right here, but you might have gone about it in a different fashion. So let's go ahead and simplify this. Okay, so what identity can I use right here? Well, I could use distributive identity right here, but I could also use De Morgan's law, because in De Morgan's law, I see that's how the not interacts with this and right here. So I'm actually going to start right there. So I know that this compound expression is logically equivalent to the following. I'm going to apply De Morgan's law just to this part. And De Morgan's law says I flip this middle operator and then I put the nots on both sides. That's what De Morgan's law says. So then I'm going to end up with the following. And so here, what I used is De Morgan's law. Oh, great. And immediately I see right here a not and a not. And I have an identity over there, which is a double negation. So I know that this is logically equivalent to that expression. So here I've used double negation. Now great. Looking at this expression right here, I see that it only involves ors. And I have an identity over here called associative, which tells me that when I have a single compound expression that involves only ands or only ors, it doesn't matter how I group my brackets right here. And so I could rewrite this as logically equivalent to that. All I did was move the brackets. So I used the associative property right here. Fantastic. Well, now I immediately see a P or P. And I know I have an identity. It's called the idempotent identity that says that this expression, P or P, is the same thing as just P, right? So the idempotent identity is actually one of those identities that it doesn't actually take a whole lot to prove it. It's kind of obvious. P or P is the same thing as just P itself. So here I could rewrite this as not Q or P. So I use the idempotent identity right here. And I could stop if I wanted to, and that looks like a pretty simple compound logical expression. It definitely involves a few less operators and one less appearance of a variable. However, I can go even a little bit further if I recall back with my definition of implication. So this thing actually turns out to be logically equivalent to So by definition of implication, I know that not Q or P is logically equivalent to Q implies P right here. So either one of these is fine. This one right here uses an implication. This one right here doesn't use an implication. It's fine. But in any case, we were able to take some of these identities over here to go from that nice complicated compound expression to one of these much simpler compound expressions right here.